Let me introduce myself. I am Vladimir Zhigalov. I'm a chief researcher of the Institute of Experimental Physics in Russia, and I also an academician of Russian Engineering Academy. My research interests are related to multi-phase flows modeling in various media. I should say it's difficult to create an adequate physical and mathematical model as the phases move at different speeds during the flow, and also phase transition occurs during the movement. These factors lead to the appearance of such physical phenomena as a friction between phases and the need to take into account the transfer on mass, momentum and energy between phases. I'd like to notice that great progress has now been made in modeling flows in pipes, and effective digital simulators have been created. Next, I will focus on this aspect in more detail. You know that multi-phase flows modeling in various media is an urgent task and has many applications in some industries. What is the main point of my paper? If the multi-phase mixture flows in a fractured medium, say in the ground, the entire flow moves through cracks, the volume of which may be several percents of the total volume. From the point of physical view, it's important to show that channel have a characteristic side of less than 1 millimeter. In my opinion, it's important to develop mathematical models that connects the flow macroscopic parameters with a lot of microscopic characteristics of the medium. To date, there are practically no relevant works on this topic. In my paper, I try to formulate the mathematical model which takes into account microscopic flows in cracks. The flow of mixture in continuous media with porosity is usually described on the basis of the well-known Darcy equation. This basic law of filtration, Darcy's law, establishes a relationship between the filtration rate vector and the pressure drop that causes the filtration flow. With such a calculation scheme, it's impossible to take into account the medium microstructural features. On the slide, we can see the Darcy equation for the component, which is written in the form where K is a characteristic of porous medium independent of the mixture properties. Another fundamental relationships in filtration theory is the mass conservation law for each component you see below. A large amount of experimental and theoretical research on the flows in pipes and channels, including narrow channels, allow us to develop numerical models of such flows. A team of researchers with the author participation has developed a two-phase liquid-gas simulator taking into account all basic physical processes. I am interested in the opportunity of using this simulator to build an equivalent conductive path of a micro-crack system. This slide presents the mass and momentum conservation within the framework of the developed physical and mathematical model. This slide presents the energy conservation equation for different phases. The right side shows the sources and sinks of the energy, which is associated with the exchange of energy between the phases. This slide shows the indexes that are used in formulas. You also need to pay attention to the exchange terms in right parts of equation. The measurement of crack structure parameters is an important element in the transition to microstructure according for the transport of mixtures in rocks. One of the methods is porometry, which is aimed at measuring the characteristic of the pore size distribution based on measurements of evaporation mass. An important aspect is also the analysis of the microporous distribution on different sections of the material. Figure 1 shows a qualitatively approximate distribution of the cracks fraction in the sample. The role of very small cracks is small due to the large role of capillary forces that prevent the mixture from moving through them. It's impossible to identify the characteristic size of cracks through which the flows mainly flow. In this paper, it's proposed to use an equivalent pipe geometric model to describe the medium microstructure. It opens up the opportunity of using pipe flow simulators to calculate mass, momentum, and energy fluxes in a calculated large-scale grid. It's proposed to use a pipeline system with one average diameter as an equivalent instead of a real branched crack system to describe the flows. With this approach, a significant number of microenvironment parameters are already included in the description of the complex filtration process in fractured rocks, such as friction against the channel wall, interfaces, friction, etc. The slide shows a model that demonstrates a microtube system with the same average diameter, which connects one side of a calculation cell with the opposite one. I should mention that various flow mode maps have been developed, such as bubble mode, shell mode, and so on, using various combinations of parameters. This was done based on published experimental studies and the multi-flow MED2 validation projects. Combination of the Freud number of the mixture with other selected flow parameters give a correct identification of flow modes, and this is included in the simulation. The main purpose of the article is to propose the mathematical models for taking into account the microstructural medium features and the transition to combined calculations, in which calculations are performed both on the macroscopic grid and for microscopic flows in cracks. The author considers this step is one of the approximation of high-performance calculations. It could be used as a complex of microscopic flows forming flows in a fractured media as a whole. As a conclusion, I would like to say that the report presents a mathematical models of the multiplied flows transfer in fractured media, taking into account the flow modeling in the medium microstructure. To my mind, the attempt to include microstructure parameters for calculation large-scale flows may have prospects due to a significant increase in the calculation speed, and this approach will provide a more believable picture of modeling in fractured media. The article also notes the opportunity of using machine learning based on the flow simulators in pipes to ensure the efficiency of calculation scheme of the entire process. Thank you for your attention, and I hope to receive feedback on this work by mail.